Hey everyone, welcome to the stream. So, I think tonight is going to be the stream I promised not to do, which is a stream where I do a lot of reading and not as much coding as I'd like, but unfortunately I'm not finding that much time in between streams to do this kind of reading, so I will try to put some code together. But yeah, I have no choice. This is part of developing an emulator. You gotta read stuff and try to understand things before you actually implement it. So, such is life. Actually, last stream, which was just a couple nights ago, there was something I was trying out, which was adding this code to my STL audio driver for what I called add subsample. And I decided to just kind of abandon this effort because the more I think about it, the more I think this is not really maybe the right approach that I want to go for. Effectively, what I was trying to do here was I was trying to hide the whole idea of resampling, which is basically the right word for what I'm trying to do. So, the Vectrex will output its samples at a certain frequency, and we need to resample it to match we need to resample the source signal that's coming out of the Vectrex audio chip to the sampling frequency we need for the actual output audio. So like 44,100 hertz, for example. And I don't think that what I'm doing here makes a lot of sense. We're going to have to address it once we have an actual signal coming out of the Vectrex's emulated audio chip, which is, we're going to call it the PSG, because I think that's what makes the most sense. It's what it seems to be called in general. Let's see if I can find here. Yeah, so you see the PSG, the programmable sound generator. We actually see it up here. The AY-3-8912, in our case it's 8912, it's just a variant of this chip here, is a programmable sound generator. So I think I'm going to call it a PSG because, that's sort of what we do. We have CPU and cartridge and all that. So, and this in particular, the CPU, I just put it in the comments somewhere, or not. But I had it here somewhere. What kind of CPU it's actually emulating. Oh no, this is the wrong emulator. Here we go, Vectrexy. That other one was my NES emulator. So here is the implementation of the Motorola 68809. And we're going to say that we're going to basically write that our PSG is an implementation of the General Instruments AY-3-8912. So, you know what, let's get started with that, actually. At least we'll get something going. Thirsty. So yeah, let's start adding that. So this will be PSG. I think it's a General Instruments. Is it? I don't even really know. I think G is the only one that, GI is the one that made it. Let's see. Sound. Yeah, I guess this is it. General Instrument AY. In fact, it actually links to this article here. So, I guess that makes sense. Yes, and we were reading this sound here. Yeah, I'm sorry. I'm just reading here about envelopes. That's one of the things we're going to have to emulate as well in the chip. Okay, so this is Malban who actually wrote this answer. Okay, that's interesting. Definitely be looking at that. And then this is that sound text file that I actually was reading. See, this one says there are 15 registers when in fact there seem to be 16 registers. So this is the data sheet for the chip itself. Right here. You know what? I'll just remove the general instruments. Programmable sound generator. Alright, I'm gonna see here. So yeah, and this document here. So here we actually see what the chip would look like. From what I understand, I think the only part that's not there for the 8912, the variant, is this part at the bottom. That there is no parallel I/O. I think that's what I read on Wikipedia. Is the same chip with parallel port B, simply not connected to any pins. So I think that's what this means. Parallel. This must be parallel port B. Could it be? I suppose so. And here they're actually showing this chip called the CP1600, which I was reading, I think, again on Wikipedia. Is it in here? Or no, maybe it was actually in this document. That I think when this chip was developed, it was developed with this chip here to drive it. And then it said something about, like, you know, I think they generalized this chip or something, and normally you would connect it to something that can drive it. And in our case, it's going to be the VIA, the Versatile Interface Adapter. And I think they actually even mention it in this document, so we should see that. But here we can see that basically the clock connects here. So we're going to be obviously, you know, getting the number of, I think it's going to be, we have to figure out, like, is it, do we want to clock it for every CPU cycle, or is it some division of the CPU cycle? We just need to figure out what the frequency is for the clock in our emulator for this chip. There's a reset here. There's some information about what that does. From what I understand, it just clears all the registers to 0. BC1, BC2, so these, I forget what they are, but I think they're used to set up the different modes for, oh yeah, I think these are used to kind of like select registers, maybe? No, not quite. No, that's not what I read. Anyways, we'll read more. I know BC1, BC2 shows up when we were doing the VIA. Actually, let me see if I can. What am I looking for? Control Shift P, no, Control P, and I think it was BIOS. No. All right, hold on. will help. BIOS, I think it's in the listing or in the, yeah, maybe it's in here. Here, so we see things like this, that on via port B, we have a pin here that connects directly to BC1. And here's some code that actually deals with BC1. So there's that sound B-dir that connects to the B-dir that we saw. So here we're starting to see how, like, through the via, through port B, we can, you know, we have these memory mapped bits that effectively map to these ports. And I suppose there must be some BC2 here somewhere. Maybe not. Okay. So maybe it's not used, BC2, for us. We'll figure that out. Okay. Then here we have DA0 to DA7. So this is basically a 1 byte like register, or yeah, it's a 1 byte register. And basically in there we can store addresses and values. And I think the B-dir is for the direction of this register. So like, is it read or write? And then we have A8 and A9 here. Not sure what those are for, so we'll have to read a bit more. Another thing I note from reading is that here we can see that it talks about how this has 3 voices or channels. You can see them here, analog A, analog B, and analog C. And then these 3 get mixed together and are output to an amplifier, which then connects to a speaker. So we're gonna have to emulate this as well. And yeah, we're gonna have to like basically mix the resulting signal here, which I think is just adding them. And actually, let me just also look in Vectrexy. Yeah, there's the sound BC1 and sound B-dir that we were looking at before. Oh yes, I remember this. So there's some stuff here where these bits are like the sound B-dir, if it's not set, I don't remember this. You see that I know that there's like some kind of multiplexing with the input here, or maybe like it, you know, what could it be? If not sound direction, but sound BC1 is set, and data direction is equal to 0. In this mode, we're reading the PSG's port A, not the via's DAC. All right. Yeah. There's this thing about the PSG being the thing that's actually connected to the joystick. And, you know, at the time when I wrote this, we were not emulating it, so we ignored it. And you know, we might leave it like this as a simplification so that we don't need to necessarily muddy the waters, you know, as it were. I don't have to make it, you know, super realistic and connect the joystick stuff to the sound chip. I don't really mind kind of hiding those details behind the via's implementation and keeping the PSG totally separate. But we'll see. We'll see if it actually makes the code more simple. I doubt it, but you know, maybe. Is there any other PSG code in here? Looks about it in here. Here I have a note connected to sound output line via divider network. No idea what that means. Alright, we'll take it one step at a time. So, the principal element of the PSG is the array of 16 read-write control registers. These 16 registers look to the CPU as a block of memory, and as such occupy a 16-word block out of 1024 possible addresses. Okay, so basically what it's saying here is we have a 10-bit address that we can form, 8 bits on the common data address bus, so that's the 1 byte there, the 8 bits from DA0 to DA7, and then we saw those 2 extra lines on the chip A8 and A9 up here, down here. Looks like those all together, these here are used to make a 10-bit addressable range. 10-bit address, 8 bits and 2 separate bits, A8 and star A9 are decoded as follows. Star A9 is not provided on the 8912. Okay, so in our case, it's actually 9 bits. I do wonder what, and then here A8 is 1. And I think I read that, we're gonna see here. The 4 low order address bits select one of the 16 registers. So here, they use to select the register number, R0 to R17, 8. It's kind of funny. Why wouldn't it be R15? The 6 high order address bits function as chip selects to control the tri-state bidirectional buffers. When the high order address bits are incorrect, the bidirectional buffers are forced to a high impedance state. High order address bits A9, A8 are fixed in the PSG design to recognize a 0-1 code. High order address bits DA7 to DA4 may be mask programmed to any 4-bit code by a special order factory mask modification. Unless otherwise specified, address bits DA7 to DA4 are programmed to recognize only a 0000 code. A valid high order address latches the register address, the low order 4 bits. So a valid high order address latches the register. So if you put 0000, at that moment it will latch the 4 on the bottom and use that as the current register effectively. In the register address latch decoder block. A latched address will remain valid until the receipt of a new address, enabling multiple reads and writes of the same register contents without the need for redundant readdressing. Okay. So from a point of view of emulation, I think that we can pretty much ignore. I don't think I've seen A8 be connected. You know what? Actually, let me bring up that schematic that I have of the Vectrex itself, and we might get a bit more information from that. I guess paint.net. Yeah, I thought I had some highlighting on one of these, but anyway. Here it is. I don't love this schematic, but let's see if we can understand something. Okay, so here we can see, okay, my highlighter. That is not super cool. I have like a yellow. Okay, whatever. How did I do this last time? Blending mode, multiply. Just want to do like alpha blending. Okay, multiply. All right, so we have here PB3 from the VIA. So this is the VIA chip here. And PB3 connects to BC1. PB4 connects to BDIR. So I think those are the two that we saw clearly in our code here. BC1 and BDIR, that's on port B, PB3, PB4, see, 3 and 4. So that makes perfect sense. We've got those connections clearly there. We have here, it shows a clock connection, but it doesn't show what exactly. Yeah, you see, this is what I mean about this schematic. It's not really clear what we're looking at. It's showing that it's connected directly to the VIA from its clock, I guess. Maybe we have to follow the clock input for the VIA chip. Anyway, we'll see. I think, you know, since most things seem to be driven by the same clock as the CPU, we can probably just start with that and see how it goes. Maybe I'll find the info somewhere. So there's this. Here we can see not clearly that the 8912 has these 7 connections here. So, you know, we talk to the VIA via the A PA, which is the A register, and that's basically the data address register. So it looks like we would use those same ones to send information directly to the AY chip here, so that's good. And I mean, it makes perfect sense. This is how the CPU will actually end up. This is the CPU over here, and basically by sending data through these memory mapped registers, we can go through and send to the sound chip. Now, there's probably, I'm guessing it's one of these, that's it, it's through PB3 and PB4 that we're able to say whether or not this data reaches to the sound chip or not, I think. Or maybe it always reaches it. I think that's what we were seeing, right? Basically everything goes through there. PA, and then we have PB over here. This is used to drive, has nothing to do with the audio. You see it completely skips. So the PB register skips the audio chip and goes up and drives all the rendering stuff, which we pretty much took care of. So let me see again. What do we do with A? Port A. I think I called it port A. Yeah, so far we're only using port A for joystick stuff. And I guess that makes sense. Oh, no, that's not true. We also use it to feed the integrator for the rendering here, for controlling the beam. Okay, so here we see audio. kind of follow this back. Volume here, so I think that's the physical volume controller. So I'm gonna do this here. Volume controller here. Okay, so this up here, I'm gonna guess that what we're looking at here, okay, these must be the three, yes, all right. These three outputs here are the channel outputs. That's, I guess, why it's called CHABC, also known as the voice outputs. We should write that here. Let's choose red. No, let's choose something something that can stand out a little bit. Orange. That does not work. Channel/voice outputs. And like it looks like it gets mixed over here and connected to ground over here or something, or connected to a resistor anyway. Just like in their image. It doesn't really matter too much. I just want to show that it gets mixed here. And then comes out into the volume here. And this part here, I'm not quite sure what I'm looking at. Is this the... I don't really know what I'm looking at on here, because we see that the data, this bus here continues out P0, P1, P7. We come into this chip, the MC14008. What is this chip? IC301. P8. Oh, that's the DAC basically. There's the digital to analog converter here. Interesting. So this is the part that's used to drive the rendering hardware. So this is just kind of like a pass-through in certain modes. So I'll just put a little note here, this is for rendering. And I'll put that this is the DAC. Okay, and then right here we see where, okay, the bottom here. All right, let me see if I can like make this a bit more clear. I should have done this on another layer. Anyway, whatever. here we see these I/O ports. I'm not sure what this, the I/O ports, did we see that here? Maybe this is what it meant by parallel I/O here. Anyway, this goes to those pots at the bottom to query the state of the controllers, of the buttons and the analog. Go to joysticks. PDN. Oh, because of the layer. Okay. Oh, why not? Yeah, I totally should have put everything on a layer. Like an audio layer or something. Oh well. Ah, look at that, BC2 is up here. And A8 is here. But I'm gonna guess that these are always held high or something. I think I may have read that somewhere. Hey, what's up, Will25? Yeah, see, it looks like it's connected to a 5-volt here, so the resistor. So I'm gonna guess these are probably just held high because A8 is supposed to be 1, and I'm gonna guess BC2 is 1 because it doesn't need it to be anything else in the case of the Vectrex. Alright, so I'm going to reread this again because I think this is kind of perhaps the good place to start for implementing the interface here. So it says the Vectrex uses 15 registers, even though it says 16. I think it's more, I think it is 16. To communicate with the 8192, by storing values to these registers, you program the chip to make sounds. And the best way to write out to these registers is with the BIOS routine byte to sound chip. So let me just take a look at that. Okay, let's go to the actual address. We might be able to. Sound bytes is F27D. Copy bytes to sound chip. Byte to sound chip. There's probably, okay, it must be this one here. Sound byte. F256 sound byte. All these routines cause a byte of music data to be written to the music chip. SoundByte stores a shadow copy of the data into this range, and SoundByte X stores a shadow copy into a 15-byte area pointed to by the X register. SoundByte raw does not store a shadow copy of the data at all. Okay. Willie asking, mind if I ask what do you use to stream? No, not at all. I use OBS. Just classic OBS. I know there's like a version of OBS that, because I'm using, what's it called again? I don't remember anymore. That extension, it's been so long I haven't looked at it. But the extension that shows like which followers, when people follow me, it you know, plays stuff. And let me see if I can get that. Extensions. Streamlabs. So I use Streamlabs, and I just basically use it so that I can show followers when they follow and subscribers, although I've only ever had one. So and And so Streamlabs actually offers like a custom version of OBS that has like more stuff in it, but you know, I never bothered to install it. I read that some people have had some trouble with it, so I just use classic OBS with my own setup on there. Are you streaming off 2 PCs? Not just one. I have 2 screens, which is why I keep looking off to the side here. But yeah, it's just one PC. So are you looking into streaming? So here we can see store the register select byte into port A. So whatever value is in A, which of the 15 sounds, so I guess it is 15. Which of the 15 sound chip registers to modify is in A? And then we put that into port A of the VIA. B, the byte of sound data, so B is the actual data itself. So we wait. We then do a load 19 here, so sound BDIR on, BC1 on, mux off. So this is very important here. So this is basically how we will figure out how to configure the VIA to talk to the PSG. Yeah, some of my buddies wanted to watch me while playing but not taking it serious, just for fun. That's cool. Yeah, it's actually really easy to get set up. If you have any kind of modern sound card, you'll want to set up OBS to do to like enable hardware transcoding, so that you don't use up your precious CPU cycles like the way I do, because I have a shitty old video card. It's like for me, OBS uses, see, like right now it's using 40% of my CPU. Like all my CPUs, you know, leaving me with about 60% for everything else. Generally, I mean, it's okay. I'm not gaming or anything, and it doesn't normally cause any problems for my streaming uses. But yeah, I can't wait to upgrade my PC. It is my plan for this year, or maybe yeah, hopefully this year. We'll see. By the end of this year, I'd like to upgrade my machine. And then I can actually transcode in hardware, like on an NVIDIA card, hopefully. So let me just take a look at this here, because this looks really interesting. BDIR on, BC1 on. Basically, it sounds like these 2 bits. I mean, you know, there's basically like, it's kind of like a multiplexer. It selects 4 states. Although BDIR is really about the direction for the, like, it controls which direction the sound chip goes in. But it's kind of like also used. It's really crazy here. If it's on, and BC1 is on, but the mux is off. Yeah, this is really strange. Gotta figure this out. You want to upgrade your PC parts? So expensive. Yes, exactly. That's exactly right. That's exactly what's been holding me back as well. I want to upgrade, you know, but I definitely need to upgrade my video card, and when I look at the prices, I just don't feel like spending any money, you know what I mean? And I don't feel like buying just other parts, because, you know, you kind of want all of it right at once. I need a new motherboard, new CPUs, new video card, new RAM. So yeah, I hear ya. Okay, so here's the mux enable. It's also on part B, of course. So this line, BDIR and BC1, are the important bits for figuring out how all this plays out. That's this one here, SH. I got an i5 as well, but I don't have a GTX 1050. See, I think your GTX 1050 can do hardware encoding, right? So you should be okay. Okay, I think I recall now. It comes down to the mux. When the mux is on, the lines connect to the video, like the video hardware, the beam, and the integrators to drive the beam. But when the mux is off, then the four lines, the four lines. I think it's 2 lines, connect directly to the audio chip. That's what we should be seeing here in this crappy picture. I clearly have not spent enough time looking at this picture. I thought I would see the mux more clearly on here. Maybe it's this thing here? 4052B. Yeah, look, I think IC302. I think I saw it. Whoops. IC302 4050B2 or MC14052B mux. So this is the mux here. So let's see if we can understand this. Ground. So there's the two selection connections right here. And basically, it looks like it will choose between the bottom set here in one. Okay, it's got a bunch of ins. So here's one here. Okay, 1, 2, 3, 4. Why are there? Oh yeah. Bits 1 and 2. On port B. So bits 1 and 2. So here they are. These are the mux selection bits. Maybe I should use a different color for mux stuff. And there they are. They connect this way. And then SH also. So what's SH here? It's also here. Okay, so that's the enable disable. That's why it says dis here. That's disable. These are the selections. You know what? Just give me a second. I'll be right back. All right, sorry about that. All right, so yeah, where were we? Before I had to go, it's okay. We were looking at this mux. Basically, we have these two selections here and an enable disable of the mux. Now, mux off. So one thing I'm noticing here is, if I look at this code here, when the mux is enabled, we have, like, basically we have these two selectors, so we have basically four possible selections, right? And 0 goes to the y-axis integrator. So if we start from the y-axis integrator here, and we kind of follow it, that maps to this out 1A. And so if we can kind of go continue there, we see that case 1 here, so this will probably be 0 is A, 1 is B, so 1B here. And that's supposed to be the X, Y offset. So let me see if that makes some sense here. It's up here, it's split down here. I guess that makes sense. I don't know. They both, so one connects to X, Y, and one connects to X. So I suppose that makes some sense, right? And then 2, which would be C, is the Z axis. C goes to Z, yeah. And then here, the one I wrote this comment, connected to sound output line via divider network. Line via divider, I don't know what that means, but basically connected to sound, that should be D, which is up here, and sure enough, it does connect to sound. So that sort of makes some sense, right? Now, one part I'm not quite understanding is, like, what is this output here? I don't know what this is. And then the other question I have is, what does it mean for the mux to be disabled? Because we clearly have code that's like, if the mux is disabled, to do stuff related to sound or to the pots here. Also, I guess what that means is that when the mux is disabled, those same lines now get values from the pots down here. I think that's what it means. Let me see if that makes some sense. Update pot value if mux is enabled. Otherwise it keeps its last value. No, okay, so it's actually when it's enabled. Enabled as well. So far I don't have any case where the mux disabled means anything, but for audio it looks like it needs to be disabled. Let me see if I can make some sense of that. So if the mux is enabled, Got our audio chip here. We got our mux here. SH. Okay, I'm not sure. I'm not. There's a part here that's missing, and I think part of it is my lack of understanding of this diagram, or maybe just a lack of information on this diagram. But what I'm getting though is when the mux is disabled here, when this line here is disabled, we are then getting values directly from the audio chip. Otherwise, it looks like we kind of skip the audio chip on the data bus. That's what I think is happening. But I don't really know why. I don't see how that works. Maybe it's something like when the mux is enabled, data comes back through the bus here, and then that kind of overrides what goes on in the chip, or something like that. Otherwise, the chip is able to. I don't know. That doesn't seem to make a lot of sense. And another thing I don't get is this sound output here and how that relates. Maybe this is another case though. This might be I saw something about this that you can control. I think this is that special line where you can control the volume through this bit. I think that's what this is about. And it's not directly, it has nothing to do with the sound chip directly. This is something where the CPU can play around with the volume and actually create digital effects, like play waveforms, for example, something like that. So I think I can, for now, ignore this. All right, I think we have still enough we can go on. We can kind of build from what we have. Just sort of getting this picture in my brain of how this works. Okay, so this is where we were. And yeah, based on this diagram, I think what we're gonna have to do is we're gonna want to probably have an instance of the audio chip directly in the VIA. That's probably gonna be the simplest thing, so that we can drive it. We're gonna want to send values for BC1 and B direction, or at least use those to determine what happens in there. And the clock, and then the PA values. Yeah. Sorry if I'm jumping around so much. It's just sort of how my brain works to kind of absorb all this information. Kind of keep rereading things and working through them. That's right. Yeah, okay. I'm looking, so this is basically giving me a clue to the protocol with the chip, and I'm probably going to find this in the spec sheet as well, but basically you store your register select byte, and then I think you have to like basically strobe BDIR and BC1, it seems, because see here we turn them on. Then we store that into port B here, which will basically send those bits into the audio chip. Then after that, we load 01 in here to turn BDIR off, BC1 off, and MUX still remains off. So it's really these two that turn off now. And then we store that. So I suppose this is what makes it read the value. So now we go into the registers, like on the PSG, we've now figured out which register to select. That's probably how that works. Let me see if I can find that then in this document. No, not here. Okay. So here we see the clock feed the noise generator, the tone generators, and the envelope generator. Okay. Conditioning of the register address latch decoder and the bidirectional buffers recognizing the bus function required. Inactive latch address, write data, read data is accomplished by the bus to control the code block. The function of each of the 16 PSG registers and the data flow of each register contents are shown in context in Figure 2 and explained in detail in Section 3 Operation. The basic blocks in the PSG which produce the program sounds include tone generators, produce the basic square wave tone frequencies for each channel, noise, produce a frequency modulated pseudo-random pulse with square wave output, combine the outputs of the tone generators and the noise generator, one for each channel, provides DA converters with either a fixed or variable amplitude pattern. Fixed amplitude is under direct CPU control. Okay. Which can be used to amplitude modulate the output of each mixer. Isn't just one mixer? Oh, okay, I see. Mixer comes here. The envelope can control the amplitude of each of the mixers. Okay. The 3 DA converters each produce up to a 16 level output signal as determined by the amplitude control. Okay. Two additional blocks are shown in the PSG block diagram which have nothing directly to do with the production of sound. These are the two I/O ports, A and B. Since virtually all use of microprocessor-based sound would require interfacing with the outside world and the processor display that is included in the PSG, data from the CPU bus may be read-written to either of the two 8-bit I/O ports without affecting any other function of the PSG. The I/O ports are TTL compatible and are provided with internal pull-ups. Okay. I don't really see it here, do we? Here. Oh, okay, so now I understand that there's really 16 channels that deal with sound, and then register 16 and 17 are just used to like forward to like basically 16 bits through. It would seem. All right. Yeah, so we've got data mode and address mode. This is the part that I had read about the bus direction and bus control. So that's what BC is, bus control. Bus controls 2 and 1. And see, it's here that it says these bus control signals are generated directly by GI's CP1600 series of microprocessors to control all external and internal bus operations in the PSG. When using a processor other than the CP1600, these signals can be provided either by comparable bus signals or by simulating the signals on I/O lines of the processor. The PSG decodes these signals as illustrated in the following. Anyway, I read somewhere about using a chip like the VIA for that. Okay, here, I think this is what I was looking for. Yes, and there's redundancies in the way this works. Okay, so this basically, so BC2 here, I think for us BC2 is always 1. Does that make sense? I think so. Let me see. Inactive, inactive. The redundancy in the PSG function versus the bus control signals can be used to advantage in that only 4 of the 8 possible decoded bus functions are required by the PSG. This could simplify programming of the bus control signals to the following, which would only require that the processor generate 2 bus control signals, either in BC1 with BC2 tied to a 5 volt, which is exactly what we have. You see here's BC2 all set to 1. So this is exactly our case. We only really have BDIR in BC1 and therefore only 4 states: inactive, read from PSG, write to PSG, and latch address. Okay. Let's at least start doing something like this. I don't know, this interface may change, but what had I done for, this reminds me of my clocks. Or timers, really. And then I had something too for my timers. Yeah, I think we're gonna have to do the same thing. We're gonna want to update for a certain number of cycles. Inactive, read from PSG, write to PSG, and latch address. For now, let's do this. I just want to get this in here. So we've got inactive, read, write, latch address. Zero, 1, 2, and 3. Right. BDIR and BC1. What did I do in here? Right. We'll call it mode. I prefer that. Yeah, and maybe instead of this, we'll actually want to set values in an actual bit mask.
There's a hole within my soul. What will fill this emptiness inside of me? And am I to be satisfied without knowing? I wish for a chance to see my all I need.
Okay, so this, we should be able to then just get the mode by effectively, I should just do this. Maybe not call this mode bits and just call it like PSG mode like we had before. Anyway, something like this. Okay. And then latch address here, we're talking about the address of the register, right? analog channels ABC outputs. Okay, so this is where there's a digital to analog converter to actually produce the audio sound, so that's fine. Input output A7 to A0, B7 to B0. Each of these two parallel input output ports provides 8 bits of parallel data to from any external devices. And these are test bits. Okay. Okay, one more thing. Yeah, so I'm interested in these DA ones here. I don't know what to call it. DA. DA set DA. I guess I should call it DA. Need a reset. Maybe I'll move this down here. Yeah, I'm not sure if this makes sense what I'm putting here. Having a write and a read function. We'll see. Because I don't know. Maybe I need like basically two states here, two registers, like the latched version that gets read and written to. Yeah, I don't know. Let me think a little bit more. what I'm thinking is that when you read and write, we just always use a latch, and then when we do our update, depending on the mode, we decide whether to copy or which direction to copy from. Maybe something like that. Let me see. If we do a read, and the latch value gets whatever is in DA. If we write, then DA gets whatever is in the latch, I guess. In fact, isn't this going to be more about this is about reading and writing to a specific address, of course. Okay, no, that's not right what I'm doing here. Right, okay, no, okay, this is not right. It is going to be more like DA gets a value, here we return the value. And then we have registers that have meaning. Okay, so for now I'm just going to keep it really simple, and I'm just going to do something like that. Well, this will change for sure. So I think latch address means that we set whatever's in DA into here, and then read and write will be something like, this is a simplification for sure, but we'll say like that, and read would mean DA is the opposite. Okay, it's a good start. Oh, actually it says bus timing is related to the bus control. So maybe not how I'm doing it, which is on a clock. Since the PSG functions are controlled by commands from the system processor, the common data address bus, DSNDA0, requires a definition as to its function at a particular time. requires definition as to its function at any particular time. Now, this is accomplished by the processor issuing bus control signals. Previously described, defining the state of the bus. The PSG then decodes these signals to perform the requested task. The conditioning of these bus signals, control signals by the processor is the same as if the processor were interacting with RAM. 1. The processor outputs a memory address, and 2. The processor either outputs or inputs data to or from the memory. The memory in this case is the PSG's array of 16 read-write control registers. Right, the memory mapped one. Okay. The timing relationship in issuing the bus control signals relative to the data or address signals on the bus are reviewed in general in the following section and in detail in section 7. While the state flow for many microprocessors can be somewhat involved for certain operations, the sequence of events necessary to control the PSG is simple and straightforward. Each of the 3 major state sequences, latch, address, write PSG, and read from PSG, consists of several operations indicated below by rectangular blocks defined by the pattern of bus control signals BDIR, BC2, BC1. Inactive, output address, inactive, output data, inactive. Address and write data to PSG sequence. Address and read data. Inactive goes to output address, inactive goes to input data, inactive. The functional operation and relative timing of the PSG control sequence are described in the following paragraphs. In all examples, BC2 has been assumed to be tied to logic 1. Okay, this is actually very interesting. Address PSG register sequence. The latch address sequence is normally an integral part of the read or read sequences, but for simplicity is illustrated here as an individual sequence. Depending on the processor used, the program sequence will normally require 4 principal microstates. Send NACT inactive. Oh yeah. Inactive, right? That's this state here. Okay, so actually, this is more of a state machine, technically speaking. We're expecting that on each cycle, we would have to go through inactive, then, you know, latch address, I suppose it's supposed to be. Then inactive and then read. So here they've given the names, completely different names from the ones that were here, which is kind of annoying because here they call them inactive, read, write, and latch, and then here they call them inactive, output address, inactive, output data. That's okay. We understand what it means. Send NACT, send intac, put address, 3 put address on bus, 4 send NACT. Note within the timing constraints detailed in section 7, step 2 and 3 may be interchanged. I don't know if I have to really go this far though. But this would explain, I think, what we were seeing over here. See, BDIR off corresponds to inactive. Maybe I'll write it here. It'll help me. This is the kind of thing where I can't do this, right? Oh no, I can. Okay, good. So like on would mean latch address. Nice. Off means inactive. Then read on-off is read. On-off is write. Store data byte. Store data byte. Why does it say here read sound chip status? Question mark. Don't know what this one's about. That looks, yeah, there's a question mark here because whatever. Then store data byte here, so we store B into via port A. And okay, so we want to put this value in B in there. We do on off. It should be right, yeah. And then we do inactive again to make it actually. So there's this little state machine that we have to go through normally. So apparently section 7 will talk about timing constraints. Like basically what I'm wondering about is whether to keep things simpler, I should just do like manage my little mini state machine directly in the functions that set those two values. And I might be able to do that more easily because we know that those are basically like rather than have these one functions to write each value this way, I can have a single function that's like write the values of bdir and bc1 at once, and in there handle the state machine every time, you know, immediately basically, like without even waiting for clocks to pass. But then again, maybe the timing makes a difference in terms of the audio, and it probably does. You know, we want to make sure that, I guess we want to make sure we're not like sending, you know, changing and sending data too quickly or something. I guess I'll have to see section 7. Let's just go take a look. Where's section 7? Here. Oh, it's all here. Clock and bus signal timing. Okay, I don't think this is helpful to me. So there's just a bunch of examples and stuff. A lot of stuff about interfacing. Examples of how to read and write to it. Microprocessor interface. Let's see here. Right. Okay. Okay, so these are the details of the actual registers with their sounds. So we're not quite there just yet, and then we're back to this here.
Jump out, feel it in the will. Can you talk about deep sea?
Yeah, I'm not sure. I'm thinking about how important it is to like to do this properly. Basically, this is not really correct. The sequence that they keep showing here is you have to first go into inactive, then go to like you can then write, let's say for writing data here, you know. So you first set yourself into inactive, so you set, you know, those two bits to bdir and bc1 to 0. Then you put your output address on the data line. The data line's like your 1 byte value. Then you go back to inactive. So I think at the point where you go back to inactive, this is when it latches the value. See, output address means latch address. So you latch it, then you must go back to inactive, then you do this, and you go back to inactive here. Which is a bit strange, this last one here. But I guess you have to be in inactive for it to kind of keep functioning. Yeah, I don't know. I don't know if I want to do it this way. I guess I should. I guess I need a little state machine. Sucks a little bit, but you know what? I'm gonna stop here and just make a little note about making that state machine here. I'm gonna say to do, don't do it this way. We need a little state machine, store current state, current mode, and you know, point mode, and you know, implement state edge. What page is this? Oh, page 14, okay. Yeah, so this shouldn't be too hard. Basically, I'm just going to store the current mode. We're going to start at inactive, and then we're going to see as we cycle. When we are in inactive and we go to latch address, then at that moment we'll do this. And this way we'll just make sure that we go through these motions. And we're going to want to be in inactive, I think, for... I don't know. I don't know if we need to... Like, the fact that we have to end in inactive, I don't know if that's important, because it is only when we're in the inactive state that like I really wonder about this last state. Is it important? You know, is it really important? Not sure. like maybe what it is that the effect of taking in the, I think maybe that's what it is, like the effect of taking the output address happens on this edge here, and then here when we do output, we go to output data, we're waiting, and then once we go to inactive, that it's at that moment that we read the data that's been output. That's probably what it is. Yeah, I guess that makes sense. Yeah. Because well, anyway, I mean, in this code, it actually stores the value before activating the mode, so. Oh no, that's not true, you see? We store the value in port B here. Oh no. Let me see if I can make sense of this. Store register select byte. Then on, which is latch address. We enter latch address there. That's it. We go latch address off, and so that's basically, we've actually already put the value on port A. So in this case, the data has already been put there. That's interesting, because see here they say send NACT, send latch address, put address on bus, whereas here it's put address on bus first. So this is kind of not in the same order that's typically done. Depending on the processor used, the program sequence will normally require 4 principal microstates. Okay. But anyway, I think doing the job on the transition to inactive probably makes some sense. Maybe the safest way. Okay, so I'm gonna stop here, guys. I might do some work on this between now and next stream. Maybe advance this a little bit, because there's really a lot of work. And I kind of want to get this audio stuff done. So, but you know, I'm also busy, so I might not get that far. So we'll see. So thanks for watching, and see you next Tuesday, most likely.